And before that, we'll have to see something known as eigenvalue decomposition. So the answer to that was actually which I was hoping all of you will give, because all of you have done two prerequisites, which is linear algebra and machine learning. Both of them teach you principal component analysis. So I was hoping that you'll give that answer. Now, can you give that answer? He already, of course, gave that answer. Does that make sense? Okay, so we'll relate it to that. So, but before going to principal component analysis, we look at eigenvalue decomposition. How many of you have seen eigenvalue decomposition before? Okay, quite a few of you. Okay. This is very straightforward. So let u1 to un be the eigenvectors of a matrix A, and let lambda 1 to lambda n be the corresponding eigenvalues. Okay. Now I'm going to construct a matrix U such that the columns of U are these vectors u1 to un. Is that fine? What U looks like? And now I'm going to do this product. I'm taking A, the product of the matrix A with the product of with the matrix U, where U is this, right? It's the all the eigenvectors stacked one after the other. Is this fine? The next step, I'm just pushing the matrix inside. If you know the 4 different ways of multiplying a matrix, you will know that this is correct. Okay? Or else for now, just think that you can just push the matrix inside. Okay? Now what is this? I can replace them by the lambda 1 u1 lambda 2, because A u1 is equal to lambda 1 u1 by definition. Okay? Now can you write this again as a product of 2 matrices? One is of course the matrix U, and the other is diagonal. So the diagonal matrix will come first, or the matrix U will come first? How many of you say U will come first? How many of you say the diagonal matrix will come first? The sum is never 1. Okay. So it's going to be like this. Okay. And you can write this as U lambda. So U is again the vector, the matrix containing the eigenvectors of A, and lambda is a diagonal matrix where every diagonal element is the corresponding eigenvalue. Now this is what we have so far. A into U is equal to U into lambda. Now suppose U inverse exists. I'll assume that U inverse exists, and later on I'll tell you under what conditions it exists. Then I could write it as this, any of these 2 forms. In one case I am post multiplying by U inverse, in the other case I am pre multiplying by U inverse. Okay. So this is known as the eigenvalue decomposition of a matrix, and the other way of writing it is known as diagonalization of the matrix. Right? You take a matrix, apply some operations to it so that the result is a diagonal matrix. Is this clear to all of you? It's very straightforward. Okay, and again eigenvectors play an important role in this. Now the important question is, under what conditions would U inverse exist? U inverse would exist if the columns of the matrix U are linearly independent. Okay, do we know the columns of the matrix are linearly independent? Yes, because it's a set of eigenvectors, and we already saw the proof that the eigenvectors are linearly independent. Okay. Okay, this just follows whatever I said. Okay. Now, do we need a proof for this? Slide 19 we did this. Okay, I didn't realize it. Okay, fine. Now, if A is symmetric, the situation is always more convenient. Why is it? What would U be? What is an orthogonal matrix actually? Okay. So the eigenvectors are orthogonal. So we have this situation, right? Suppose I want to do U transpose U. Okay, this is how that operation would look like. Okay. Now what is the ijth entry of the resultant matrix? Is the dot product between the ui and uj. Everyone gets this, right? The ijth entry of this product is going to be the dot product between ui and uj. This dot product would be dash if I is not equal to 0, j. 0, okay. And okay, there is no point in this. Okay. So each cell of the matrix Qij is given by the dot product, and it is going to be 0 if I is not equal to j, and it's going to be 1 if I is equal to j. Okay. So U transpose U is equal to the identity matrix. That means U transpose is the dash of U. Transpose of U. And of course inverse also. Okay. So U transpose is the inverse of U. And it's very convenient to calculate. What's the complexity of inverse? So now you appreciate that that has a high complexity, and in this case, if the matrix is orthogonal, that means it's a collection of orthogonal vectors, and the inverse just comes for free, right? Okay. So now given this situation, and don't read the hint as if this is going to help. But yeah, what can you now say about the sequence, the same sequence that you saw earlier? So I have given you that the EVD of A is equal to U sigma U transpose, where U is the collection of the eigenvectors and sigma is the eigenvalues, or diagonal matrix containing the eigenvalues. Now what, given this and ignoring the knowledge of the first section of this lecture, can you tell me something about this series? What would be the nth element of this series? U sigma power n U transpose, and you arrive at the same conclusion, right? But I was talking about this operation, right? So if we can say something about this matrix, then we can say something about the series. What can you say about this matrix? If the largest eigenvalue is greater than 1, as you keep raising its power, that value is going to explode, and hence the entire product is going to explode. Less than 1, that product is going to vanish, and everything else would be less than that, right? Remember, it's the dominant eigenvalue. Okay, so everything would be less than that, so that product will vanish. Okay, so the same conclusions you arrive at, right? So that's why I want to do these sections again. So you would have done these in linear algebra, but you would have not arrived at these conclusions from a very different interpretation. But I want to focus on the interpretations that I care about. How many of you have seen this series in the course on linear algebra? Oh, you have, okay. But I don't see why anyone else would teach. This is not required. This is only required for some things that I want to do in the course, right? That's why I wanted to do this section. So everyone is comfortable with eigenvalue decomposition. It's a very simple stuff, right? I mean, there's no proof or anything involved there. We just use some properties of eigenvectors and eigenvalues and do it, okay? Now there's one more important property of eigenvectors which we'll use today. So let's see what this means, right? You have a matrix A, which is an n cross n matrix, okay? And you're interested in computing this value, x transpose Ax, where x belongs to Rn. X belongs to Rn, okay? So what am I trying to do here? Of all these vectors possible in Rn, I want that vector which maximizes this quantity. What is this quantity? Scalar, vector, matrix, tensor? Scalar, okay. Such that x is equal to 1. This is the problem that I have been given to solve. Why, it's not clear as of now, but suppose this is a problem I am trying to solve. Or the inverse of this, which is minimize the same thing. Of all the vectors in Rn, find the vector which minimizes this quantity subject to these constraints. Then the solution for this is given by the smallest or largest, okay, the solution is the smallest eigenvalue of A, and x is the eigenvector corresponding to that. So if you're trying to minimize, the solution is the smallest eigenvalue. We need to clarify that. If you're trying to maximize, then the solution is the largest eigenvalue. Is that clear? And the value of x would be the corresponding eigenvector. So largest eigenvector is the same as something that we have defined today, dominant eigenvector, right? So let me just repeat so that there's no confusion. Let's focus on this problem. The solution to this problem, that is the x which will give me the maximum, which will maximize this, is the dominant eigenvector of the matrix A, right? Is that clear? Fine, okay. And if you want to minimize it, it's going to be the smallest eigenvector. That means the inverse of the dominant, okay. So there's a proof for that. I'll not go over the proof. You can take a look at it at your own leisure. So what has been the story so far? The story has been that the eigenvectors corresponding to different eigenvalues are linearly independent, okay. If you are dealing with a square symmetric matrix, which is something that we'll deal with soon, then things are even more convenient because the eigenvectors are actually orthogonal, okay, and they form a very convenient basis. And now we're going to put this to use when we talk about principal component analysis.